So today we're pleased to have a local new professor, Schneider, talk to us about neutrinos.
That's super cool. So in this talk, I'm going to cover most with an experiment called Coherent CAPTAIN Mills. This may be the fourth or fifth time something like this has been presented in the department within the past year. So who here has seen me or somebody else give a CCM talk here?
A lot of new faces. That's
okay. Yeah, good. We have at least maybe around 50% new to this information then. So I'll still go through all the intro stuff. And this may run a little bit short, so feel free to jump in and ask questions. There are some new details. So Coherent CAPTAIN Mills, TAMU is a 10-ton liquid-argon Cherenkov detector. So we're searching for neutrino signatures and other PSM signatures using the scintillation-light and also Cherenkov-light signatures. So we're light based liquid-argon detector. And in fact, the largest liquid-argon light-based detector by photocathode area, and certainly the most densely instrumented. We've got about 50% photo coverage. So these are all 8-inch TAMUs, 200 of them facing into this interior volume. And our detection volume is basically a tuna can that's about 1 meter by 2 meters. So this gives us a 3-ton, a 7-ton region inside of this volume. And there's 3 tons of liquid argon on the exterior that we count as our sort of veto region. So we have some instrumentation as well in this outer volume to catch things that are kind of coming in, so we can tag backgrounds and such. So we're still midway through our data taking period. We've taken 2 out of 3 years of run data. Yeah, we basically are here. So the previous year didn't have any data, and neither does this year, both due to kind of issues with the accelerator. But we did take some engineering data far earlier and already published some physics results. So even with this sort of very limited data, which was just a couple weeks worth of data taking, we were able to place some new constraints on physics scenarios. So since then, we've both been taking more data. We've upgraded the detector to have more of these sensors. This version I showed you was kind of the final or current version of the detector. And then we've been redoing sort of all of our data processing things. So actually reconstructing all of these little light signatures inside the detector is quite a challenging task to figure out what's, yeah.
What is 120?
So yeah, this one has 200 PMTs in it. The previous version didn't have the top or the bottom set of PMTs, and so there were 120 of them. So that's what CCM 120 is the sort of prototype detector. Thanks for asking. So yeah, so these results that we initially published were from that engineering one run with the prototype. But right now in 2025, we've done all sorts of calibrations and things, and we're now working on machine learning reconstructions and building the sort of statistical analyses for doing physics searches. So CCM, I mentioned, is a neutrino detector primarily. We're located near a neutrino source. So this is the Lujan target facility at the Alamos Neutron Science Center. Basically, what's happening is there is a linear accelerator that is accelerating protons up to 800 MeV. These are then fed into what's called a proton storage ring. Essentially, multiple pulses from the linear accelerator are stacked on top of one another to create a pulse that's very intense and also very short in time. So there's some compression in the timing of the pulse that's done inside the proton storage ring. This then goes over to a warehouse. The beam is bent 90 degrees down into the earth, and then this hits a large tungsten target, which is located here. So we're 23 meters away from the target in this detector hall. What's not shown here is the absurd amount of shielding that surrounds this. So there's many meters of steel and concrete and lead shielding around the tungsten target to prevent a lot of the radiation from actually reaching us. So there's a lot of stuff that's produced in these interactions besides just neutrinos. So what's actually happening is when you have this proton collision, you get a lot of neutrons, but also a lot of pions, both charged and neutral. So the charged pions, the high minuses, almost all of them are captured, but the high pluses will actually come to a rest in the material and then decay once they've stopped. The time constant for that is pretty short, about 26 nanoseconds. These proton pulses are 290 nanoseconds long, so really it's quite quick compared to the duration of that wave. And these paired pion decays are going to give us our flux of neutrinos. As these are coming to rest, they decay in a random direction, and so we get neutrinos kind of isotropically emitted in that target. In that decay, we also get a muon. This will also decay to neutrinos, but the time constant for this is much longer, about 2.2 microseconds. And so what you can see here is this is the energy spectrum of the different neutrino species. You have a monoenergetic flux of muon neutrinos coming from the plus decay, and then you have a continuous spectrum of the muon antineutrinos and electron neutrinos coming from the muon decay. The timing for those components is very different. The prompt muon neutrino decay gives you something that very closely follows our triangular beam pulse, whereas these two components are much more delayed. And so by just looking at the timing, we can actually understand something about the flavor of the neutrinos that we're observing, or potentially other processes that might be involved that could produce other things. Okay. So as far as proton beam dumps go, there's actually quite a few other accelerators out there that are doing similar things. The Lujan facility is actually somewhat ideal for this kind of thing because of the sort of sharp timing. So the pion decay at rest process that I described earlier provides us with a very clean flux of neutrinos. The energy spectrum and the timing is all very well understood. There's not a lot of other processes that are involved in that. There could be backgrounds. The main thing we really have to worry about is other things produced in the proton collisions like neutrons. And so I guess the ordering here is a little bit strange, but this short duration of the pulse is quite important for getting rid of neutrons. So neutrons are much heavier and they will move more slowly from the target. And so essentially by just stepping back from the source, you can then separate things out by timing. The light neutrinos will arrive first and then the slower neutrons will arrive later. So you want as many protons in a short period of time as possible. So this plot is showing the sort of number of protons that you get as a function of time for different accelerator sources. And you can see this is the sort of Lujan pulse here. And this plot is showing the same thing, but cumulatively over time. So when our actual pulse ends at 290 nanoseconds, is this dashed line here. And you can see that the only accelerators that are really beating us are JPark and SMS. And the reason why we're operating here and not one of those is primarily due to space constraints. We have a large warehouse where we can put a large detector, which is not necessarily possible in facilities. Okay, so beyond neutrinos, we are targeting other physics scenarios. So in these proton collisions and in producing a lot of these pions, and so we can potentially search for things that are very rare processes. So other pions decaying, radioactive, and other things, producing new particles that are very difficult to detect. So some of the physics searches that we're undertaking are search for axion-like particles. So this is showing in terms of the axion coupling to gamma rays and the mass of the axion has available parameter space that hasn't yet been constrained. So this little triangle space there. And CCM sensitivity is this curve. So we can reach in and actually constrain some of this or potentially observe something. We're also performing searches for dark matter. This is a leptophobic dark matter scenario. Again, this is the mass of the dark matter as well as the coupling on the y-axis. And you can see that CCM is carving out new parameter space that goes below the atomic density line. We're also looking at signatures that are relevant to anomalies that have been observed. I don't go over this in any detail in this talk, but there have been some neutrino experiments that have had both anomalous excesses of events and anomalous deficits of events. And one of the particularly interesting things is electromagnetic excesses at neutrino experiments at short distances. These are the short baseline neutrino anomalies. And so this is a scenario that introduces essentially a portal where you can produce new particles through the pion decays that can then potentially be absorbed in neutrino experiments. And so it offers a potential explanation to the mini-boon anomaly, which is this shown in this blue curve. So that's the preferred region of parameter space. And the potential CCM constraints are shown in two red lines there. So we can actually say something about the compatibility of this model with one of these anomalous observations that we've seen in the neutrino sector. And we can also make some statements about the atomic anomaly, which is essentially looking at a rare particle that could be produced in nuclear de-excitations that has a mass of 17 MeV. So this is another anomalous observation that we've seen in the field. And CCM has some sensitivity to that as well. What's common to a lot of these things is that there's an electromagnetic signature that's in sort of the MeV to tens of MeV scale. And that's very similar to the neutrino energies that we're looking at. So this is sort of a perfect setup as far as looking for these sort of tens of MeV electromagnetic signatures. So we're probing both those and lower energy nuclear recoils. We're sensitive to a wide variety of scenarios that include these explanations to anomalies and also some accelerator-produced dark matter scenarios. As I mentioned before, the way that we're producing neutrinos or other rare particles is through proton interactions on the tungsten target. This target is actually optimized to produce neutrons. So this is a neutron facility. Most of the experiments there are looking for neutrons and performing measurements with them. But those are sort of the major end up being the major potential background for us. And so we want to put or remove as many of the neutrons as possible from our samples. The primary way that we do this is through shielding. So there's a lot of shielding between us and the target. There's this diagram, although none of it's easily readable in the labels, most of this material here is actually shielding. Only this tiny little cylinder in the center is the tungsten target. And we place our own additional shielding outside of that to block as many neutrons as we can. So this both removes the neutrons from, or prevents them from reaching the detector, but it also attenuates the flux and slows them down. So even high energy neutrons that do reach the detector, if they lose energy soon enough, they may actually not make it to the detector quickly enough to end up in our samples. But the things that we're looking for are very light and interact very rarely. And so they're going to be moving at the speed of light and reach the detector promptly. So this is essentially showing just that. This is a plot showing different things that may reach the detector as a function of time. So the solid line is the time signature of the proton pulse itself, whereas the dashed line here is when the neutrinos from that prompt pion decay would arrive at the detector. This black curve is showing the time distribution of the neutrons as they would arrive at the detector if there was no shielding at all. So you can see even with no shielding, there's quite a significant difference between these two curves. And so just by being 23 meters away, we can have pretty significant separation between the signals and backgrounds.
And what's the timing resolution?
So we digitize at about 2 nanoseconds, and it ends up being that, yeah, we can get about 2 nanosecond reconstruction precision. There's of course some caveats there, but yeah.
But 2 nanoseconds on the scale.
Exactly, yeah. So we're doing pretty good as far as timing, and that's actually, one of the major design constraints of this experiment is we had to get digitizers that were capable of this and choose sensors that were capable of this.
What is the difference in the pulses, like the gap between the proton pulses?
So the beam operates at a rate of 20 hertz. So it's actually many milliseconds between pulses. But yeah, that's a good point. So the the beam will produce a lot of neutrons that go into the hull, which can then activate material to produce radioactive isotopes, and then these will then decay, potentially produce background gamma radiation in the detector, amongst other things. So it's only longer-lived isotopes that really cause a problem. So most of the short-lived isotopes, by the time we get to the next beam, are gone. But we do actually see a big difference in the background rates when the beam is on and when the beam is off. It actually doubles our background rates.
So it makes the neutrons without shielding slower than.
It's really just the mass of the neutron. So the proton beam is only 800 MeV. So yeah, we do see neutrons in simulation at least up to around 600 MeV. But even if you put an 800 MeV neutron in there and you do the calculation, there is still a significant timing difference. I think it's maybe, I might be wrong in this, but maybe about 70 nanoseconds is the like the hard, physical delay. You can't get any shorter than that. So that's why there's such a big gap here. It looks a little more than 100. So, yeah, with the shielding though, we observe this. This is actually real data from CCM. So this is what we observe once we close the shielding in, is that's much attenuated and much more delayed. So the detector design basically is PMTs all inside of, or looking at unicanons full of liquid-argon. As I just mentioned, there's a fast sampling time, so we digitize it 2 nanoseconds. We end up getting sensitivity to physics interactions with 100 keV for recoils up to potentially 2 GeV for neutron-neutron annihilation. You'll notice that inside the detector, some of the PMTs look a little bit different. This just has to do with the fact that liquid argon scintillates in the very far UV, which is a wavelength that literally doesn't get through the PMT glass. And so we need to wavelength shift the light into the visible so that it can be detected. So this sort of, these lighter colored PMTs are coated in a wavelength shifter material called TPB, or tetraphenyl butadiene. We left some of these uncovered and made the detectors heterogeneous in this way so that we can actually discriminate between different wavelengths. It's not just the scintillation light that's produced in the detector. There's also Cherenkov-light, which is broad spectrum. There's a major advantage to being able to discriminate between those two. So the scintillation light is really most of the photons that are generated in the detector. It's about 40,000 photons per MeV of deposited energy. Whereas the Cherenkov light, we only get about 700 photons emitted per MeV. One of the nice features, though, about the Cherenkov light, if you can detect it, is that it's directional, whereas the scintillation light is isotropic, and it's also very prompt, so it potentially gives you even better timing. So basically, by looking at differences in the arrival time of the signatures of the detector, we can try to isolate Cherenkov light. So if we compare what we observe on coded PMT versus uncoded, you can see the coded ones, there's a lot of overlap between Cherenkov and scintillation signatures, whereas for the uncoded tubes, there are delay. And so we can tag Cherenkov light pretty reliably by looking at the difference between those two. Okay, and the reason why this is important for us is that nuclear recoil-like signatures mostly are not, they don't have the charged particles producing the Cherenkov light, whereas electromagnetic signatures, all of the constituent charged particles that are going to Cherenkov light, so we can do some particle discrimination. So this works out essentially with for the signatures that we're interested in the electromagnetic side. They're higher energy, they produce both of these components of light. The primary background for them is neutron scatters, which only produce both side for nuclear recoil. Looking at lower energy ranges, it only produces one of these two. Background for this is low energy beta decays, and that background produces both. So worked out in terms of which backgrounds are producing which kinds of light, that we can use this for background pretty reliably. So One of the very challenging things about this detector is actually modeling the light propagation in liquid-argon and also all the reflections, the wavelength shifting, and the timing of it. Liquid-argon has absorption and visible. There are contaminants in the detector. There's relay scattering, V scattering. The wavelength shifting has a time structure to it. There's a specific absorption profile of the wavelength shifter and of the materials in the detector, reflection, angular distributions. So it's rather difficult to get all of this right simultaneously. So there was a significant effort put into actually building the optical propagation model and calibrating the detector so that we're mapping the data. So this work has now been done. This is one of the two papers that's linked up here. So we had a recent publication on this calibration work, which implements a new fully differentiable optical simulation to enable us to be able to optimize this algorithm. So this calibration uses a radioactive source at the center of the detector. So we have a sodium-22 source that produces a 1.2 gamma ray and a positron. So we get a little more than 2 MeV worth of positive energy in the detector. And then we essentially just try to match our simulation to that data. So what this plot is showing you is the sort of long scale time structure on the top right. So you get the number of photoelectrons observed as a function of time. And so we get here both the sort of initial peak that comes from the singlet state of the triplet light. So argon scintillation light comes in two forms. They are differentiated by spin state. One has a prompt decay time and scale decay time. But measurements of this disagree. We have contaminants in the detector that can affect this as well. So we had to measure it in situ. You can see that we've got very good agreement there. And zooming in on the shorter time scale, we've also gotten very good at describing some of those finer grained time features as well. Yeah. So we then start zooming in, and we want to start looking for the Cherenkov-light. We can then compare our coded tubes to the uncoded tubes. So what you can see is the coded tubes that have that wavelength shifter coating on them. They have a pretty narrow rise time. So from this sort of t equals 0 to the peak of that distribution is a little more than 5 nanoseconds. Whereas for the uncoded tubes that don't have the wavelength shifter, this is it's a while to get to this peak. And this is basically just happening because in this scenario, the coded tubes get the production of visible light or the conversion from UV light right on the surface of the PMT, so it goes in immediately. Whereas these uncoded tubes have to rely on wavelength shifting material somewhere else in the detector to convert the light when it propagates to the PMT. So that's why we get the delay. But you can see it here in both the data and the simulation, which both agree quite well. And if we then split this out into the scintillation and Cherenkov components, you can actually see that at very early times, we're mostly observing Cherenkov light. So with the sort of existing basic event reconstruction infrastructure that we have, we can tag the Cherenkov light almost by just looking at uncoded cubes of these early regions. I should note that these are very low energy events as far as Cherenkov light is concerned. I think the Cherenkov threshold, energy threshold for electrons with argon is a little over 300 keV. And these are events that are at the sort of MeV scale and below. So we're operating very close to the production threshold for this kind of light. And so the fact that we can identify it, it's been quite impressive, at least something that the community's been looking to do for a while. So this is, many events aggregated together, but we can actually do this on a per event basis. So we can take individual events and then tag single photons that we you can do this with some machine learning reconstruction, but a simpler way to break this down is to just look at sort of the number of PMTs. So we know that the uncoded PMTs are the ones that are going to have that Cherenkov light very early on. And so what we can do is we can look at the number of uncoated tubes that receive one of these early hits. And so this is showing a breakdown where we have the data in black, the simulation for all types of photons, whether they're UV, scintillation, visible, Cherenkov, in blue, and so that matches quite well in terms of the number of uncoated tubes that are hit. But then if we then remove the Cherenkov-light and just look at the scintillation plus random backgrounds, we can see that in the pink, there's a large discrepancy between data. So if you just look at one photon on one uncoated tube, very likely white. And if you require an event to have more than on a coated tube, basically guaranteed that it's coming from Cherenkov-light. And so this is showing kind of another way to look at it. The Cherenkov-light is emitted in a cone. So it's the directional distribution is very important. And this is basically looking at the opening angle between pairs of uncoated that are hit. And again, it shows the data compared to the simulation, which agree. And the second pink line here is when you remove Cherenkov, which basically this is telling the Cherenkov-light is contributing essentially all of this distribution. And you can see that this is the number of detected Cherenkov photons as a function of the true energy for that electron. And we're still getting Cherenkov photons as we approach that production threshold, which is down here. So we've achieved per event Cherenkov identification, and we've also done it below 1 MeV, very close to the production threshold. And a statistic, I guess, it's not in these slides, is that we were able to do this about 10% of the time, which sounds maybe bad, but is impressive in the context that only 10% of the surface area has these uncoated tubes on it. So we're actually very efficient at identifying the Cherenkov-light.
Off the free one. Let's go back one to 2D histogram. What's going on at MeV there? It seems to be right, like.
So there's two contributions here. I didn't make this plot myself. This comes from a graduate student, so I can't speak exactly the contributions that are in here. But it may be that these are sodium-22 decay events, which produces a 1.2 MeV gamma and a positron. So it could be that the 511 keV pairs are influencing this. So that would be my first guess, but I don't actually know. Okay. So this is basically kind of arguing that we can do very accurate reconstruction in the detector with electromagnetic events, especially at very low energies for what we're interested in. The BSM signatures that we're looking at are at the tens of MeV. So identifying the Cherenkov-light there and performing the reconstruction gets even easier as we go. We're also performing some standard model measurements. The electron neutrinos that are produced through the muon decay, we're actually trying to perform a measurement of the interaction cross-section. So what happens is an electron neutrino interacts with an argon nucleus to give you an electron plus some atom that is different from the original one. And you most often get this excited potassium nucleus. So this cross-section has been measured on carbon before, never yet a liquid-argon at this sort of energy. So this energy regime below 50 MeV is relevant for supernova detection. You can see here the comparison between the rest spectrum, which is shaded regions, versus the supernova neutrino energy spectrum. So measuring this is going to be relevant for future experiments with looking for supernova events using this type of detection technology. So for the cross-section prediction, we use a piece of software called Marley. I won't get into too much detail about it, but there are two sort of main contributions that we look for. These basically are different types of transitions that are happening at different angles. Our prediction here is sort of flat, and then these are sort of two other predictions that are making essentially different assumptions about the transitions. It has a different angular distribution in terms of the angle of the outgoing electron with respect to the neutrino. So there's some complexity in this, in that we both don't know the total cross section, but also there are some uncertainties in the final sort of angular distribution of these events. So if we're able to reconstruct the total cross section, that would be great, but also if we're able to help constrain the sort of relative normalization of some of these different transition types, that would also be very helpful, especially because for supernova, the directional reconstruction is quite important. And I guess, yeah, the model predictions for this vary by up to a factor of 2. So for CCM, with 5 tons of liquid-argon in the interior, so we've subtracted off some of the exterior volume, 107 tons that's inside that tuna can, and assuming our sort of 3 years of data taking and a 75% efficiency, we expect to see about 150 interactions across 3 years. So the largest source of uncertainty is the neutrino flux, which we expect to be around 10%. We also expect some systematic errors that come from the resolution threshold. And so putting all of this together, we do have a pretty sizable sample, but the main concern is actually going to be backgrounds. So on the actual beam itself, we have prompt neutrons that are produced, which I mentioned before. We get rid of these through shielding and time cuts. We also have activation of material around the detector, which can give us radioactive byproducts. We get rid of these through quality cuts, removing things that appear to be coming in from the outside. And we can also measure them sort of in situ. We have a lot that we take that come before the beam pulse arrival to constrain some of those. But the non-related backgrounds are cosmic neutrons and Michel electrons from cosmic muons. So a muon can come in and stop in the detector, and then its subsequent decay into an electron will produce an electromagnetic signature that's quite similar to the electron-neutrino charge current interaction that we're interested in. So this is almost an irreducible background in that you have an electron with tens of MeV of energy. And so you'd think we wouldn't be able to distinguish these except statistically. And if you just take the statistical argument, you can see here the spectrum of the electron neutrino charge current. So this is energy and MeV on X. The blue energy distribution is in the blue versus those neutral electrons. So there's some difference there, and so you can statistically differentiate between these. But it's not ideal having some kind of irreducible background like this there. So assuming that it is irreducible, we can essentially measure the flux integrated cross section to about the 16% level. But there is another option. So the majority of these electron-neutrino interactions will produce an excited potassium-40 nucleus. There are other potential nuclear byproducts, but this one in particular can give us an advantage in terms of differentiating these kind of events. So this potassium-40 will actually, it will re-excite and emit gamma rays from the nucleus, which can then be tagged in the detector. And normally this would be quite difficult because you have an electron track that's occurring, in the vicinity of this gamma ray emission, right? They're right next to each other. They're happening at the same time. But it just so happens that the potassium-40 has a metastable state. And so if in the sequence of transitions you end up in this metastable state, It is a time constant, I think, of what, 480 nanoseconds. And so for us, at least, that's quite a significant time delay. So if we see an electron then followed by a small gamma ray emission, then this is sort of a dead ringer that this is an electron neutrino charge current interaction as opposed to a shell electron. Thankfully, these transitions produce gamma rays that are of reasonable energy for us. So we get transitions that produce gamma rays of several MeV. And so these are actually pretty reasonably taggable by the detector.
Do you have like an estimated tagging efficiency?
So this is yeah, something we're working on actively right now. We've transitioned from my slides to Marisol slides, who's a graduate student on CCM. This is coming from a presentation that I think was given 1 or 2 weeks ago. So this is something we're actively working on right now. So this process, we actually get a K40 nucleus about 70% of the time. And we get a K40 nucleus that where the transition sequence goes through this metastable level about 41% of the time. So it's a pretty significant proportion of these. And given that we have 150 of them and a large background or a background rate that is larger, I think, than or comparable rather to our signal rate, this is going to be pretty critical in improving the precision of this measurement.
If the potassium does not reach the metastable state, then because of the other transitions, then will we lose the charge current interaction events?
Yeah, so we'll still use them in the statistical analysis. It's just that they'll be split into separate samples. We'll have a sample essentially that has tagged gamma rays as well as their large times and energies, but then we'll also have a sample that didn't have them. So there is still statistical power in a bin that has both these like signal and large background contributions. So that's kind of the scenario.
And then the ones that don't have the tagged potassium will be, you'll have your quote unquote irreducible background.
Yeah, exactly. But there is still some statistical power in there.
Right.
So we'll do the full, combined likelihood analysis to get everything. Yeah. So this slide has some details that I won't go over, but the main takeaway here is these are some simulation events that have these gamma rays in them. So this is the main scintillation pulse that comes from the electron. This sort of part of the signature here is the triplet light, that longer-lived scintillation state. That has a time constant of around 500 or 600 nanoseconds. And then this little blip here is the one of the delayed gamma rays. And so you can see here another example of a higher energy gamma ray that was closer in and stacked on top of this triplet light. So the task now is to be able to identify these gamma rays, tag them, and then build the full analysis that incorporates all of this information. So we're still working on this, but we expect significant sensitivity moving from this really small background, significant overlap at the distribution level, to something that has, very low backgrounds. So we're coming to the end of how much I was able to paste from our recent internal collaboration talks. But we are currently doing a lot of work in machine learning reconstruction for this. So far, we've trained reconstructions for the sodium-22 decays that are at this sort of MeV scale, and started training on sort of tens of MeV electron and positron reconstruction. So we've been using just a very simple transformer architecture where we tokenize pulses, reconstructed pulses individually, and then feed them into a transformer stack sequentially. And even this simple architecture gives us pretty good performance in vertex reconstruction. So we're getting around a 3 centimeter resolution in position with this. But significant improvements are, likely achievable if we improve the architecture of this. So this work has kind of just been starting, and things haven't really been optimized for this detector and this reconstruction specifically. One of the other things that we're starting to pursue is temporal semantic segmentation. I didn't put the canonical liquid-argon projection example up here, but semantic segmentation is just being able to identify parts of an image or associate them into like a particular category per pixel level. This is done for liquid-argon projection chambers, which almost essentially just take static images of the charge that's observed in the liquid argon. They drift the charge over to an observation plane. And so semantic segmentation there is very analogous to other image-based machine learning tasks. In this case, however, we're working in sort of the temporal domain, so it's a little bit different. But at least from what we've read and studied so far, we believe that it should be possible to do the same thing, these kind of time signatures, to basically identify at a per pulse or per time step level what percentage of this is coming from different particle species, or at the very least, what percentage of this is coming from different particles specifically. Because there is a lot of sort of redundant information in the time structure of these events, right? We have the initial singlet pulse, but that also gives us this sort of long time scale triplet information as well, which is this sort of primary way that we get pile up in the detector, is the singlet pulses overlapping triplet pulses from previous events. So this should be a tractable problem, in particular for a couple of the reconstruction scenarios we're considering, this electron neutrino charge current, as well as identifying Michel electrons that come from muon. That muon produces a large light background as well. So this will be, if we're able to train this type of semantic segmentation, will be very useful input for subsequent reconstructions. And can even be applied to some of the newer liquid-argon time projection chamber experiments like SBND, the short baseline neutrino detector, and DUNE, the deep underground neutrino experiment, which both have photon systems like CCMs that have very fine-grained timing resolution, although their spatial coverage is lower than CCM's 50%. We think it should still be possible, and so yeah, that's kind of some of the next steps for the web. That's all I have for you guys today.
Any questions for Austin?
Do you have any background projection after taking this Cherenkov-light? Remember, you had a background projection for 120 done. And like you had a real measurement, and then you made a background projection based on that for 2.
Yeah.
So how much improved?
It's a very good question. We don't know yet, but we're very close to an answer. So Marisol and Christian have both been, who you may have met, there are two graduate students on the experiment, are both looking at so-called beam backgrounds. So for context for everybody else, when we take data, we digitize basically 16 microseconds worth of data, even though we only have a 300-ish nanosecond window that we have. And we take a significant amount of data that comes prior to particles arriving from the beam pulse. And that basically allows us to get a very precise measure of the steady state backgrounds, things that are coming from cosmic rays, things that are coming from activation detector hole. And we do expect significant reductions, and we should be able to do a comparison. Yeah, probably in the next couple of weeks. It just depends on how much time they have. So.
A question about the beam profile, I think it's around slide 7.
Yeah.
That one. Yeah. So you show like a triangle shape for the Lujan beam.
Yes.
Are the other ones, are the rectangles just simplifications, or are they?
They are there's almost simplification, there's sort of simplifications, but they are closer, much closer to rectangles.
Okay.
So maybe a rectangle with some rounded edges. But yeah, the Lujan pulse is unusual in its triangular shape. I can't actually speak to how the square pulses are produced, but I do know that the reason that we have a triangular pulse is that in the proton storage ring, there's a compression stage where we actually, compress the pulse in time. And that goes, into the proton storage ring, but that pulse doesn't make it out of the proton storage ring for several cycles. So we actually stack multiple pulses from the linear accelerator onto that. And so you have one pulse that starts out like this, and then on the second pass, it's a little wider, the third pass, it's a little wider. And if you stack several hundred of these, you end up with that triangular shape. That's how we get there.
The neutrino flux uncertainty of 10%.
Yes.
And you said you didn't seem to be worried about that. That was fine. I mean, is that going to stay like what it is for the time being?
Yeah, I mean, I think we're not making any significant effort to try to pin it down. I would guess that we probably need to add some instrumentation upstream in order to get a better constraint on it. Yeah, I mean, since there's significant cross-section uncertainties, it's kind of hard to constrain, like, in situ in the detector. I don't know if it's going to get much better than that. I think SNS reports like a similar.
Yeah, they're similar, but they're kind of down with a D2O experiment.
Yeah, that's right. Yeah. So yeah, without doing something dedicated like that. Do you know if the SNS constraint will actually translate to a improved prediction here? I don't actually know where they for the neutrino flux. I don't know.
I think they want to bring it down to like 5% or so.
Yeah. I guess what I'm saying is I don't actually know where the uncertainties come from. So,
for where they.
So if they're constraining something fundamental that we might benefit from.
Okay. Oh, you're asking, is it specific for them?
Yes, SNS target.
Market.
Mercury?
I thought right? For you is tungsten. And
For us, it's tungsten. I know JPark is mercury. I actually don't know about SNS.
I feel like it's mercury. Actually.
It's less relevant for us.
So Lance is going to be upgraded in the near future. Are there plans for what you will do while AMP is happening, or are you going to take the detector somewhere else?
Yeah, so we don't have concrete plans right now. There are some potential options. We could use the detector for engineering studies. If there is ever space at SNS, we'll absolutely move the detector. No questions asked. Let's say from this plot, you can see it's 10x improvement in power. And depending on where you are, has lower neutron backgrounds. So it would be very nice to move the detector. There's still a lot of analysis to work to do. So we can probably go through another 2 generations of analysis work before that's kind of tapped out. We're also working on building new experiments in the same detector hole. So I think the lamp upgrade is nice, at least in there. It's not going to shut things down completely for that long, at least as far as I'm aware. So you never know with these things, but yeah, the hope is that this will be able to be run again.
About the charge current, can you do the anti-neutrino channel?
We don't have anti-electron neutrino production because the
Can you do the flux? Okay. Yeah, it's muon neutrino and anti-muon neutrino.
yeah, so the energy is too low for muon neutrino charge current. So we're below the muon. So that's why we can't do charge current.
I see.
It is possible to do neutral current measurements, So there's the coherent elastic neutrino nucleon scattering process. But this is a very low threshold for detection. So the nuclear recoil energy that you get is mostly below sort of 100 keV threshold that I've quoted here. I'm uncertain if I actually put this in the backups or not. May not be in there. But basically, the reason why we have trouble going down below 100 keV is because the scintillation light that's produced in the detector, although the argon is completely transparent to it, there are contaminants in there that absorb it. So through primarily oxygen and nitrogen contamination, those two will absorb too many of the photons before it reaches the PMTs. So for interactions in the center of the detector, they're essentially invisible to the detector. But if you have an interaction close to one of the PMTs, you can potentially observe it. There's complications there, flips and reconstructions, backgrounds, and things like that. So it's something we're still going to attempt. But yeah, you can potentially do recurrent measurements. The flavor discrimination, sort of the timing differences between the different components. And we're building a second detector that will be better at that. So.
It's Mercury, I just checked.
Hmm?
It's Mercury, I just checked.
Okay.
So one other thing, so the Cherenkov would not improve your coherent because it's too low. It's 50 kV on this and this is half a.
So I mean, it could maybe improve the rejection of these like beta decays. The thing is, most of those are at higher energies, so the class of events that you're rejecting are events that are sort of clipped off by that size of the detector. So I don't actually know if there's enough Cherenkov-light produced in that little tiny stub of an event to really get at this. So we will try it, but it may. I suspect it won't have much impact.
No other questions? Second speaker again?